Hello interwebs, welcome to Let's Fix Computers. Man, I do love it when I'm desperate for simple content for the channel and a HP laptop with no power drops in for repair. So let's have a look at this and see if we can make it work again. I'm gonna plug in a charger and we get no charger light at all. And the power meter is showing nothing in particular. I think that's idle power consumption of the Type-C to DC cable I'm using. Yeah, when I unplug it, nothing happens either. Alright, so we've got like literally nil, although there's a tiny little wobble at the bottom of that disappeared after I unplugged it. Okay, let's get the back cover off of this and do some stabbing. Alright, usual HP stuff. We've got to remove the rubber strips, so we'll just dig under here. You need to get right under the adhesive for these. Here we go. There's the rubber, and then there's like a plastic layer. You need to go all the way under the plastic until you get to the actual plastic of the case itself. If there's any adhesive here, you need to pull up the adhesive as well, and then you get a nice clean tear like that, which will go back on nice and easily. Right, disconnecting battery. This laptop's had some upgrades done to it. Looks like the SSD has been changed because that's not OEM, and we've got some memory in here as well. Looks like a 16 gig RAM kit. Now let's turn on the multimeter. I'll put that into resistance mode, and we're going to check some rails. So I'm going to pick a nice ground point. I'll go onto the back of a large capacitor here. So there's the stripe there on this capacitor. So this side will be the negative. And we'll check the, let's see, we want to find our main power rail. So here's the CPU, and here is CPU V-core, because we've got inductors and power stages going into the CPU. And then we've got a big capacitor here, and the positive side of this capacitor, the trace for that goes around into these MOSFETs. So that's going to be our main power rail. Let's see what that's doing. And we have a main rail short. You'll love to see it. Excellent. All right, let's roll the intro, and then we'll take a closer look at that, and we'll find out why we are shorted. See you after the cut, folks. Okay, so firstly, let's take a closer look at the measurements that I just took and explain how I got there. So we're under the microscope now, and I've zoomed down on the CPU V-core area that I was measuring. So here's our CPU under the cold plate there and the heat pipe. And if we look to the left of it, we've got these power stages here, which are these squares, and they go through inductors, and then there's capacitors, and then that all feeds into the CPU power rail, which is this big, huge mass under here, with lots and lots of vias peppered through it, because this is a big, high current rail. So they use, they put it on both sides of the boards and stitch it all together to make a big chunk of metal there. So if we go back, you can see on our power stages here that these have got this big fat trace leading into them there, and it comes down and leads in here as well. And we know that that is going to be the power input, because there's going to be a ground here somewhere as well. And the big question is, okay, well, is that power or is it ground? Well, we know it's power because this capacitor here has a stripe on it indicating the positive side of the capacitor. So if this is a positive, then this has to be a power rail and not a ground. Whereas on the other side of it here, that's going to be a ground. And just a side note on capacitors and knowing which side is positive, most of the capacitors that you're going to see in a laptop are either going to be ceramic capacitors, multi-layer ceramic capacitors like these little brown dudes, which are the ones that usually fail, or they're going to be tantalum capacitors, which are these large black square packages here. Here's another one. Now, a multi-layer ceramic capacitor, this is non-polarized. It doesn't have a positive and a negative. It goes either way around. It's symmetrical inside. However, tantalum capacitors are polarized. They have a positive and a negative, and the positive is denoted with a stripe. So let's see if I can put that at a slight angle to show the stripe on it. There we go. If I put that at an angle so we can actually read the writing, you can very clearly see the stripe across the positive there, which goes to the stripe on the motherboard. Same goes for this guy. We've actually got a positive marker there going to the stripe on the motherboard. Now, the reason why I point this out so heavily is that the very classical looking capacitor, the cylindrical electrolytic capacitor, which we don't have on this motherboard. Let me grab one. I couldn't find one, so here's a desktop motherboard. So these are electrolytic capacitors, and the important thing is that the stripe on an electrolytic capacitor denotes the negative, not the positive. So that's why I'm pointing this out, just as a friendly reminder. I'm pointing at stripes indicating the positive, but on traditional electrolytic capacitors, it's actually the other way around. The stripe is the negative, because standards. So moving on. So we've established that this bit here is going to be a power rail going into the MOSFETs that power the CPU. And the input to the CPU vCore MOSFETs is going to be the main power rail, because this is a very high power rail going into the CPU. Therefore, it needs to sit on the biggest rail in the laptop, which is the main power rail. So with all of that context out of the way, I put my black probe on the negative of this capacitor, and I can measure the main power rail by measuring the positive of it. And we get that 0.34 ohms that we're seeing there. So with a short circuit on the main power rail, the first question we need to ask ourselves is, do we have a high side short into the CPU? So a high side short would be these packages here. These are power stages, and they will be dual MOSFET packages. So there's two MOSFETs in each one of these, the high side and low side, forming a buck regulator. And if the high side MOSFET has failed, it will have failed short, bridging the main power rail directly into the CPU. This puts 19 volts into the CPU and kills it. So if you have a high side short into your CPU, you're basically toast, unless you want to replace a CPU. So we really want to know if that's what we're dealing with now to save ourselves a lot of time. But this is difficult because the CPU has an extremely low internal impedance, a really low internal resistance, which means it will look like it's shorted to ground anyway. So how do we know if we're shorted through here? Well, what we'll do is we'll find that the resistance on our shorted rail should be different to the resistance at the CPU. So we're seeing 1.35 there, sorry, 0.35. So if I come over here and we measure after the power stages, great. Now we're seeing about 9.8 ohms. So that's fairly high for a CPU, but I think they've been creeping up over time. Usually I expect to see, like 3 or 4 ohms, maybe 5 ohms at the CPU. In which case, 9 ohms, that's fine and dandy as well. It's very clearly different. Now, you can apply this same test for the GPU because that suffers the same problems. But the problem is that GPUs are extremely low resistance to the tune of less than 1 ohm. So at that point, you're going to have a hard time telling the GPU vCore resistance from just a short circuit. But you can still do this. You're probably going to find that a GPU is about like 0.5 ohms. And if your short is 0.3 and your GPU is at 0.5, there's a good chance that it's not a high side short. But if the short circuit that you're measuring is identical to what you're reading on a GPU, then you might have a high side short into the GPU. The good news there is that GPUs are pretty tough, and there is a good chance that a GPU will survive a high side short. So if you've got a high side short into your GPU, keep going and actually replace the MOSFET, because there is a good chance that that is salvageable. However, this laptop doesn't even have a GPU, so we're going to move on. So, let's take the motherboard out of the laptop because we need to look closely here now. So, I'm going to zap all of these screws out and we'll get this thing out of the chassis. Okay, the board is out. I'll take off the heatsink as well because it's probably going to get in my way at some point. And also we can just put some new thermal paste on it while we're here. Right, so I had a peer at the motherboard when I initially took it out there. So when I inspect the motherboard, the main thing I'm looking for is just scorch marks. You know, sometimes you can see a burnt out component or a black mark, you know, a skid mark or something where something has exploded. And occasionally it really is that easy and you'll know exactly where the fault is. We've seen that in a couple of videos where I've taken the motherboard and been like, there it is. On this one, I'm not seeing anything screamingly obvious. I'm looking at all of the MLCC capacitors, checking for any that look clearly distressed, and not seeing anything screamingly obvious, although there are a couple down in this area which I think look a little bit shabby. Let's have a look under the microscope and play the game of spot the fault before we inject. So looking at the board, those look fine. This one on the end here, from a distance, I thought that looked like it might have problems, but I can see it's just got a slight divot in it. That's nothing. Those guys look okay. Same with these guys. Yeah, no, there's nothing screamingly obvious here. I could spend 5 minutes staring at capacitors and maybe spot the fault first. Or I could just go directly to power injection and find out. So let's start going in that direction. So let's do the power injection checklist, everyone, which changes slightly every time I say it because I've never written it down. So power injection is a method of finding a fault on a motherboard that has a short circuit. However, before we do it, we need to ask ourselves, why are we injecting power? Well, we have found a short circuit on the main power rail, and we want to know what part is actually shorted. Cool, okay. So, do we know where we're going to inject power? Yes, we're going to inject onto the main power rail here, because we have found that this is shorted. We know it's not supposed to be shorted. Cool, all right. So, what are we expecting to happen when we inject power? Well, if we inject power here, that power is going to flow through a shorted component in to get to ground, and the shorted component will get hot, allowing us to discover it on the board. Cool. All right. Is there anywhere else that power might go that is unexpected? Okay, so where else could it go? Well, it could go into the CPU. Well, we've already checked for a high side short, and we've already established that there's no high side short into the CPU, so it's not going to go into there. All right, well, where else might it go? Well, this is the main power rail, and all of the secondary rails are connected to it. So we should probably check our secondary rails, because I've forgotten to do that. This is why we have checklists. Cool, okay, right. Let's move that to one side, and let's quickly zap over the secondary rails. So the secondary rails are basically any other inductors that we can see on the motherboard. So the CPU V-core here, this is technically a secondary rail. We've already checked that that is not shorted. So now what I'm going to do is basically just put my multimeter across all of the other inductors on the board. So let's start over here. This guy is probably the battery charger. That's not shorted. Cool. So CPU, we've already established looks right. 9 or 10 ohms. Yeah, okay. There's whatever this is. 130 ohms. Okay. There's this one here. This is an auxiliary rail for the CPU, 25 ohms. That's not very much, but it's not a short circuit. What about these guys up here? 30 ohms, okay. And 40 kilo ohms and rising. And then up here, nine kilo ohms. Okay, well that covers all of that. So those secondary rails, as I mentioned, we've got like auxiliary rails for the CPU for things like the memory controller or the integrated GPU. This one over here is probably part of the battery charger because it goes to the battery connector. Then one of these guys over here will be the memory rail that powers the RAM. And then two of them will be the 3-volt rail and the 5-volt rail. So we could identify which one is which, but it doesn't really matter right now because none of them were dead short. So we don't really care. So we can just move on. We don't have to do that maths. So because none of the secondary rails are shorted, we know that our short circuit on the main power rail, that can only be going into a shorted component somewhere. So we've made a reasonable assumption at this point that if we inject to the main power rail, that injected power is only going to go into the fault. It's not going to go into something else. If we found that, say, the 5-volt rail was also shorted, this could mean we have what's called a cascade failure, where the 5-volt rail has exploded and is shorting the main rail powering it. And that would mean that if we inject on the main rail, that's then going to flow through the 5-volt rail again to further places, to who knows where. So if we find another shorted secondary rail, we have to investigate that first and investigate why that is shorted before we solve the upstream problem. But we have no shorted secondary rails, so let's move to injection. I'm going to solder some jumper wires onto this motherboard to do my power injection. Now, a lot of people, myself included as of late, have gone to just stabbing probes for power injection, but I'm actually coming back to using jumper wires purely because I'm making a video about this. In reality, just stabbing some probes while you're holding a thermal camera is the simplest and quickest way of doing power injection. But because you're holding probes against the board is kind of inconsistent, and I want to do a good showcase to show people how this all behaves in the heat of the moment, which is very useful for people who are trying to learn so they can see exactly what the instruments are supposed to read under ideal situations. So I'm actually going back to putting on jumper wires just because it makes things a bit clearer and a bit easier to understand. So I'm going to put those on this capacitor that I've been measuring because the capacitor is a nice big object, so we don't need to worry about that being fragile or anything. So there's a ground wire. And there's a positive wire. We're all set up here now. So I've got my power supply set to 1 volt and 3 amps. And I've got my Thermal Master P3 thermal camera plugged in, ready to spot whatever gets hot on the motherboard. So I'll start recording here so you guys can see what the thermal camera sees. And I'll turn on the power supply. Okay, oops, there we go. Nice and toasty down there. Okay. Right, so there's our problem. So on the power supply, we've reached 1 volt at 2.2 amps. With a better connection into our short circuit, the voltage would drop further. However, as soon as there's any kind of resistance, the voltage will start to build up because there's a potential difference. That's what voltage is. However, the important thing is that we are pulling current. We are pushing current into this short circuit. And the thing on the board that is getting hot is over here. Let's zoom in on that. And there it is. It's a little capacitor. So let's take a look at that under the microscope and see which one it is. So what we were just looking at was this dude here. That guy was the one that was getting burning hot. So let's take a closer look. Let's lift this up and see if we can spot anything wrong with it. This is the point where everyone in the comments is just like, oh, I spotted that when you did the overview. Yeah, sure thing, buddy. Oh, there it is. That's cracked down the side. All right, well, there's our guy. So let's take that off the board. I'm going to come in with my secure HT140 hot tweezers for this. These guys struggle a little bit with heavy power planes like what we're dealing with here, but they're incredibly useful because it means I don't need to worry about having hot air right next to that plastic battery connector. Right, so I'm going to take off both of these capacitors. We want to take off the one that is faulty because it's faulty, and I want to take off the other one so I can measure it and see what value it is. Because 9 times out of 10, a group of capacitors like this will all be the same value. So let's just get some heat into those. There we go. Now, question the first. Has this solved our problem? Let's measure the capacitor that we've been working with. And yes, our main power rail is no longer shorted, so we've solved our actual short circuit. Good times. Question the second is, what were those capacitors doing? Let's have a look. So this is a pretty good textbook example of a HP motherboard here, because down in the bottom left, this is where our DC in jack connects. So we've got a cable here that goes to the side of the laptop where you plug the charger in. So let's have a look and let's just reverse engineer how this is connected up. We've got a couple of signal pins here that go to signal traces. It doesn't matter. This is for stuff like charger ID. You know, it senses what wattage the charger is and things like that. We've got some ground pins here, which are going to go through to the ground layer. And then we've got 2 power pins here, which are moving up through the board on this big fat trace up into this MOSFET. We've got a TVS diode here. This provides static protection and reverse voltage protection. So if a incorrect or incompatible charger is plugged in, then this will short out the input, protecting the laptop from a bad charger. So once we hit this MOSFET, this is our DC in MOSFET. We go through here, and then we hit the second DC in MOSFET, which is this guy here. And now we become the main power rail. We go around here and through this current sense resistor, 010, and this then becomes the main part of the laptop. So you see that pattern of 8 vias there. Let's flip the board over and see on the other side. And on the other side of the board, they connect into this big fat trace that then travels all the way across the laptop. And it goes all the way up the side, and it also goes all the way across here, all the way around, and so on. And it goes around to important places on the motherboard. It doesn't matter. But the point is, big fat power rail that goes across the laptop. So that's how our main power comes in. It comes up through these DC in MOSFETs and becomes the main power rail. However, in addition to that, once we go through those DC in MOSFETs, we're also coming up to this section here. Now, this MOSFET connects up into the battery, and this allows the battery to also power the main power rail. So this allows power to come out of the battery and into the main power rail. And to stabilize that, we've got these capacitors here. And this is where we found our faulty capacitor. So this guy here was shorted. And because that is part of this main power rail, that's why it shorts everything else on the board, despite being nowhere near it. And then the final piece of information here, which is not relevant, but just for interest's sake, is these 2 MOSFETs and this inductor. This is the battery charger. So again, from the main power rail, we can travel through these MOSFETs, through this inductor, through another current sense resistor, and up to this bit. And through these vias, this is going to connect back to here. And we can quickly check that by measuring continuity. So let's just check the continuity from here to here. And as you can see, these 2 points are connected. There's zero resistance between them. So we've got this MOSFET, which allows power to come out of the battery and into the main power rail. And then these two MOSFETs form a power regulator that then charge the battery if we're running on DC power. And the reason why we can't just go both directions is that when the battery is powering the laptop, we just run on battery voltage. But when the charger is connected, we have 19 volts on the power rail. That's too big for the battery. So we have to go through a regulator to chop that voltage down to whatever charge voltage we are putting into the battery, which will be 7.5, 11, or whatever architecture the battery is using. So that's what all of this stuff up here is actually doing. So now question the third, what was the value of the capacitor that went bang? So what do we replace it with? So firstly, I have to find the capacitors because I've put them down and lost them. One moment, please. Here are our two capacitors. So one of these is going to be dead. Okay, that is reading high resistance. So it's probably not that one. And that one is reading shorted. So that's the dead one. Cool. So that guy's dead. Let's put him out of the way. And now I'll put the multimeter into capacitance mode. And I'm going to guess 10 microfarads. It's going to be 10 or 20. And it's 10. So that's 10 UF, 10 micro symbol F. Okay. And there's our replacement guy. So I'll put some flux down there. And now we're going to position our capacitors. There's one. And there's the other. And let's come back in with the hot tweezers. That's probably good enough. I don't think that's fully flat, but I'll take it. Let's just neaten up the sides slightly. And I'll spray some alcohol on there to clean up. And finally, I will just measure again just to make sure that we are now no longer shorted, just in case there's any problems with the work I've done there. And nope, we're reading megohms, extremely high resistance. And again, just to eradicate all doubt, here's the original capacitor that I was measuring. And that guy is also A-OK. Right. Let's remove those jumper wires as well, because we don't need those anymore. And that's a fixed motherboard. Let's put it back in the laptop and see if it works. Right, that's everything back in the laptop. I'm going to put the back cover on because this chassis is super weak when the back cover is off, so just to avoid risking the hinges, I'm going to put a couple of screws in before I open it up again. And we'll plug a charger in the side. And we've got an orange charge light there, which you can't see under the studio lights, but more importantly, you can see on my Paul Daniels power meter here that we're now pulling current and the battery is charging. So I should now be able to turn it on. Yeah, I've got a power light on the side, and after a few moments we should get a HP logo. Because we disconnected the battery, it's going to ram train and stuff, so there might be a delay while it posts for the first time. So we're going to be patient. This can take like at least a minute, and a minute is a really long time when you're just sitting and staring at a black screen. So be patient, give it time. The nice thing, oh, there we go, CMOS reset. Yep, sure, enter to restart. The nice thing about having power meters like this when you're diagnosing a computer is you can look at the bar graph to see very clearly what's been going on. You can see on this where we had a current increase as the computer was on. There's the dip where it turned off and rebooted. And now we can see that jagged up and down of just the random power consumption of the computer, because it's constantly just thinking and doing stuff. And every time the CPU thinks a bit harder, it uses a bit more power. So you get that very characteristic random spiky line. And there's our HP logo. And we're booting into Windows. Right, so that's that all solved. The only other point of interest that we do need to consider as well... Oh, hi Windows Update. I hope that doesn't fail. The only other point of interest that we need to consider is the condition of the battery. Because we had a short circuit in the laptop would have been just... It would have had a vampiric power draw in it, where it's just constantly trying to power up its standby rails. And this will just drain the battery stone flat because the battery was connected. Now, a good battery should cut out when it hits 0% and refuse to provide any more power until it's charged again. However, if you've got a crap battery, a very worn out battery, or a third-party battery that's not very good, this is the ideal situation to critically discharge the battery or over-discharge it, where it dips below 0%. Because a battery is, theoretically, the battery is at 0% when the cells in it hit about 3.0, 3.1 volts. But if if something is constantly pulling power on the battery, trying to switch on, you might be able to drain the cells even lower than that, down to below 3 volts. And at that point, they become critically discharged, where the battery doesn't want to charge them from that state. So that's how you can get into a situation where a power fault like this will also give you a dead battery. Now, talking about how to solve that and how you can possibly recover a battery like that is a bit outside the scope of this video, but because it's a thing that doesn't get discussed very often, that's a bit of collateral damage that we also need to check on. So at this point now, it would be prudent for me to just charge the battery and then discharge it just to check that it's okay. Anyway, that's all I got for you today. I hope you guys enjoyed that. Thank you very much for watching, and I'll see you next time. Bye for now.